So multi-threading means the ability of operating system to support multiple common execution paths within a single process. So in each process, you can have multiple execution paths, multiple traces of execution. So if your operating system supports multi-threading, then process and thread is two different units. Process has resource, and process has its memory image, virtual address space, as before. So it has its private address space, and all of its resource, I/O device, memory, and so on. But process is no longer a scheduling unit. Instead, thread is the unit of scheduling, and it has its own state. Process has some state, but each thread in each process has its own state. The states are execution state because it has execution paths. Like process, it has ready state, running, or blocked. Blocked means it's waiting for I/O. Okay, similar to process. And thread also has its context. So here it has some thread priority, thread state, and some registered because sometimes it has to stop and save its context and resume. So it has registered and some other thread state information, and execution step because it's running. So you have user step and kernel step. So not all operating systems support multi-threading. So some of them, old operating systems such as MS-DOS or old Unix operating system, they don't support multi-threading. This is called single-threaded approach. So one process, one thread. So this is traditional approach of single thread of execution per process. So you don't have to think about thread in this case. So there is no concept of thread if you single-threaded approach. But if your operating system supports multi-threaded approach, each process can have multiple execution paths, multiple threads. There are two different approaches. One is one process with multiple threads of execution, and the other is multiple process, and each process with multiple threads. So this is more general. So in this case, it's supported by Microsoft Windows, modern Windows, Solaris, some Unix operating system is called Solaris, and modern Unix supports multiple process, and each process can have multiple threads of execution. Java, virtual machine and runtime environment support only one process, but each process can have multiple threads of control. Okay? So this shows an example. So this is single-threaded approach. This is multi-threading. This is single process, single thread, one process, one thread of execution. So you don't have to use terminology thread in this case. Process is the execution unit and scheduling unit. And you can have multiple process. Each process also has a single execution path. Okay, so this is multi-process, but one process, one thread per process. Still single thread without multi-threading, right? Because each process in a box, there is only one thread of execution. Okay, so all of these are single-threaded approach. Multi-threaded approach like Java, one process, but each process, in a process, there can be multiple threads of execution. So this is one example. More general case is multiple process. Each process has multiple threads within each process. Okay, this is for Solaris and modern Unix, and we'll look at some Solaris example. How do they support multiple process with multiple threads? So in a multi-threaded process model, So there are two models. One is process model, the other is thread, multi-threaded model. This is single-threaded process model. This is multi-threaded process model. If you look at multi-threaded process model, this is process-related information is here. Thread-related information is maintained for each thread. This thread. So let's look at process has one kind of information. So like before, process has its private address space. It's called also virtual address space. So process has private address space. Private address space we have reviewed from process slide. So each process has its own virtual memory. In a virtual memory, it has programmed. Okay. So text segment comes from execution file that has instructions. Data segment has also come from execution file. It has static variables and global variables, which we have discussed. Okay. So all static variables declared inside a file, which has a file scope, and also static local variables. Those are defined inside a function, but it's declared as static, which means you can maintain your state across the function code. So you have to allocate in a static data area. So execution file has this static local variable storage allocated. So they come from execution files. And other like heap and stack are created at runtime because heaps are dynamically allocated as you request malloc. If you free, then you deallocate. You can control. So you request whenever you need the memory. So you can use your memory more optimally. So you don't have to allocate permanently in static area. That's dynamic area heaps. Okay. So we'll look at a little bit for the heap when you talk about virtual memory and memory management. And stack is when you do a function call or a procedure call, you allocate space for each function dynamically at a stack frame. Okay? Because you don't have to allocate permanently. All these local variables are used only when this function is running. If you return from the function, you can declare. You can relate your stack frame up to stack frame because you don't have to use those variables. Those are only used inside the function. Remember, these variables are scope is only within the function. If you have a block within a function, and if you declare local variable within a block, the scope is only that block inside the function. So you can declare either beginning of the function or in a block. If you have a phrase in a C program, okay, you can limit your scope. So you don't have to allocate at the static storage, which are permanent. You can allocate dynamically at the stack frame. So these all are included in the virtual address space, virtual memory, right? Text, data, heap, and stack. And there are some read-only data and also BSS data. Those are uninitialized global variable. Read-only data, these are actually created at load time, because you don't have to allocate in the execution file, because they don't have to occupy the space. It's uninitialized, and they are initialized at load time at 0. Okay? But they are located at the static storage for this global variable. So should be common. So these are virtual address space or private address space or memory image, process image. Since you might not remember, let's look at this is virtual address space or private address space. We have this text instructions, global variable, static variable, uninitialized global variable. This is read-only data. This is initialization routine, which means all the programs should initially execute these are like instructions, but these are common routines used by all the programs. So this is This is actually instruction. These are the global. This is global read-write data, read-only data. This is uninitialized global variable. This is static area. Okay? And this is heap. This is stack. So user area has instructions, text, static, heap, stack. And some of these regions are mapped to shared libraries such as cleanup, scanf, feature shared by other processes, but they are mapped to this region. Okay? This is user area, this is kernel area. Kernel also has code, instructions, data, heap and stack. Okay? You go back and forth between user mode and kernel mode. If you do an exception, you go to kernel mode. Return from exception, you go back to user mode. Right? If you do a system call, it's a trap, you go to kernel mode. Right? We talk about exception and interrupt also. And these are process has this image, and all the threads actually run the code from this path, but they run different instructions, different control paths. Okay, but they share this memory. If one thread writes into this data, the other threads, if they read from the same address, they can read from the same data. So they can communicate through this shared memory because these virtual memory are shared by all the threads in a process. Okay, so process has this image, virtual memory, and also all the I/O resource, or all the I/O device. It has the resource. Okay, memory and I/O. Okay, they are shared by all the threads within each process. So process has this virtual memory image of memory, and it's shared by all the threads, and it has access to files and I/O device and memory. Okay, these are all shared by all the threads within each process. And OS also provides protection because each process should be independent. They should not look at other virtual memory or other I/O device. So OS provides protection. But within each process, each thread has its own execution stack and thread control block. Okay, so in a thread control block, since they are the unit of scheduling, sometimes it has to be blocked or it has to be stopped. Okay, then its register values must be saved and restored. So when it saves, it should save its program counter because each instruction run by each thread is different. Right? You have to save this state program counter, which instruction it was running before. And that's program counter and stack pointer because the functions within user area or kernel area, the function sequence are different for each thread. So they have different execution paths. So you can point to this stack pointer, another special register that point to top of the stack. These are register values. And in a thread control block, it has also other thread state and other information related with thread scheduling, which is thread state, whether it is ready to run, running, blocked, priority. Threads can have also priority, which sometimes some thread has a higher priority over the other thread. And other thread related state information is in this thread control block. But thread control block, it has less information than process control block. Process control block, it should have file table, I/O table, memory map, and so on. But thread doesn't have to because it doesn't. They are all sharing memory and files and I/O device. Okay, so much smaller, but it has its own state information in a thread control block and execution stack. So if you look at here, in a multi-threaded process model, it has user stack and kernel stack, and also thread control block. Here it has thread state, priority, and other thread related state information. And process has its own process control block. Here it has also its process state and process priority, and more information, files and I/O information, file table, I/O table, memory map, and so on. And it has its memory image. Okay. If you don't use multi-threading, single-threaded approach. There is no thread control block, no thread-related information, only process. You have process control block, memory, and user stack and ballast. Okay? So all the threads within each process share the same address space and share the resource of that process. So when one thread changes the data item in memory, the other thread can see the result when they access the data by providing address. If you access the same location, some other thread modified, you can see the result. So they can communicate through shared memory. It's not possible in a process. If two processes try to communicate, they should use some kind of signal. So one process can send a signal. Signal is actually sent by the kernel to the destination process. But the destination process can block the signal or can receive the signal, can actually set up what kind of action it will take for each signal. It can ignore, it can terminate the process, or it can actually provide some user level signal handler, so they can do their own job by installing the signal handler. So signal is another subject, but I'm not sure we have time. So if you're really curious, I can give you more background about the signal and how two processes can communicate. But it has more overhead because it's going through the kernel. Okay? But threads, they can communicate through shared memory, because they can read and write. And also they can share files. So if one thread opens a file with read privileges, the other thread can also read from the file. Because it's all shared. Somebody read, so I can read freely. Okay? So what are the benefits or advantages of thread? So thread is sometimes people say threads are lightweight process, and they sometimes use lightweight process more specifically. But thread is lighter than process. Okay, it has less information in its thread controls block, and it also takes less time to create, less time to terminate, less time to do a thread switching, context switching, and less time to communicate. So thread is a lightweight version of a process. Okay? So that's why people are using thread. Okay. There are another notion of thread in a computer architecture. They also call it multi-threading. Multi-threading. So if you look at Core i5, i7 processors, each core is multi-threaded processor. It has two register sets. It has two program counters. So you can run. So in a single core, single-threaded processor, actually there is only one program counter. If you do a multi-programming or multitasking, if you look at one time, only one process is running. You are doing interleaving. It's called multi-programming or multitasking. With hardware multi-threading, you can have a multiple program counter. Every cycle, two actually different process or thread can run simultaneously on each processor. For server processors such as Sun, Niagara 2, each processor core has 8 threaded multi-threaded, which means there are 8 program counters, which means 8 different processors or 8 different threads can run simultaneously on each processor core. And processor chip has 8 processors, 8 CPUs, and each CPU is 8A multi-core, each core is 8A multi-threaded. So 64 program counters in a CPU. That means 64 threads or process can run simultaneously every cycle. There are 64 program counters. Recent Spark is called Niagara 4. They have 128 program counters in a single CPU. It's 16 processor cores, each processor core is 8-way hardware multithread. So it's used for server because you can create thread or process for each request, and they can run on different core. They can also run on different thread. Okay, but that's hardware multithreading. We are talking about software multithreading, and this is software multithreading. We will discuss user level multithreading and kernel level multithreading, which are also different. Okay, and this is in general. We are talking about more combine both user level and kernel level multithreading. Especially it's more related to kernel level multithreading, because user level multithreading has some limitation. We'll discuss what is user level multithreading. Don't worry. Okay. So threads is less time to create a new thread. Mac is another research operating system, Mac operating system development approach. Did some study, and thread creation is about 10 times faster than process creation. So this is more lightweight. Okay? And it's less time to terminate a thread than terminating a process. Because you don't have to release I/O or memory. You can just stop, and thread has only less information. You can terminate, exit the thread more easily. So it has less time. And less time to switch between two threads. So process switching is sometimes user mode to kernel mode to user mode, two mode context switching. So thread switching, if you use kernel thread, you don't have to do a context mode switch twice. So thread switching is faster, and as we have discussed, communication between two threads are faster because you can communicate without kernel using shared memory. But process, they require signals, and operating system provides protection. Some other function for this signal handling. So if you use multi-threading, logically, it takes less time, and your perceived speed of execution will be improved by using multi-threading. And sometimes logically, you can divide a single process with multiple threads of control, and it's somewhat easier to program. It's more modular because different functions can be run by different threads. You don't have to have multiple functions in a single process, single main function, which is complicated function. Okay, independent functions can be controlled by different threads. So it's logically simple. It's also in a performance way, if you use kernel thread, it's also much faster. If the operating system supports multi-threading and scheduling states are maintained at the thread level, but some actions affect all the threads in the process, because some actions are inherently process-related. There are two examples. One is suspension, swap. So suspension, there is two different terminology. In this textbook, suspension, the author used suspension for swapping. Swapping means the process image is moved from main memory to a disk. But in general, suspension can be used for stopping the process, suspended and resume. So suspension and resume is suspension is another terminology for stop or pausing for a process. Okay? But here they are using swapping. So swapping a process involves swapping all the threads of the process, because if the process image is moved to the disk drive, the threads can no longer access their instructions. So all the threads are actually suspended as well, swapped as well. Okay? Also, the terminating a process means it's terminating exit, then process is finished, and it is in a zombie state. And it is in a zombie state until its parent collects. It's called reaping, R-E-A-P. Reap is like harvest. So zombie is it can do nothing, but it has some state information, and parent collect. It's called reap. and the meaning is same as harvest and dictionary. So until it's read, it's in a zombie state, and it can no longer execute. The process cannot run anymore, and terminating means all the threads within each process should be also terminated. But still, threads can execute as if possible. It's zombie, you cannot do anything. Right? The only thing is, parents should remove the process, and all the threads are also removed. Okay, and then it will disappear from the system. Okay, so these actions, termination or swapping, are related to process, then thread. Okay, but other than that, thread is like process. You can create a new thread, so you can fork, you can terminate, and then so switch. Let's revisit the multi-threaded application, how we use threads in real applications. So in a textbook, it shows an example of file servers. So for a file server, a new thread can be spawned. Spawned means create. You can create a new thread. As new file request comes in, you create a thread that serves this file request. And since server usually handles many requests, you can create many threads in a short period of time. And then after you serve the request, you can terminate the thread, you can destroy it. In a multi-processor or multi-core environment, multiple threads can run simultaneously. As you create a new thread, you can dispatch this thread to a new core or new processor. So they can run simultaneously. Okay? But in a single core processor, you have to run one by one. But processor with a single core, they can run only one core encounter. Okay? And in a file server, even if you implement process or thread, file server, they must share file data because some of the file requests are going to the same file. They have to coordinate their action. If you process, coordinating is more difficult because you have to use message passing or signals which going through operating system kernels. But here, if you use thread, you already share files and you already share memory. So you can share files, you can communicate through shared memory, and you can coordinate action. So if you do good programming, you can actually it's faster to use threads than process. Okay? So file server performance will be improved, or at least your perceived speed of file server will be improved. Okay? There are other examples that benefit from these multi-threaded applications. Let's think about the spreadsheets like Excel programs. So you can create two threads. One thread can do an I/O. They display menus, and they can read user input, and they can send a prompt message. Another thread can execute user command. So you can create a thread for these two different tasks. Even if you use a single processor or single user system, you can increase perceived speed of the application because before the previous command is complete, they are doing the processing of this execution. The other thread is display menu and reading user input and send prompt message for the next command. So user can type in the next command. So user response time will be faster. Okay, because these are interlinked and CPU is so fast, and we don't have to wait for this before previous command is complete. So we can improve the speed by writing multi-threaded applications. Similarly, if you use word processors such as 아래 한글 or Microsoft Word, you can create a separate thread for backup from RAM buffer to disk. Okay, and they can do a regular backup at maybe every 5 minutes or 10 minutes as you set up. And the other thread can read input. Right? So they are independent, and logically they are also independent. So if you don't use thread, then you have to do these two different functions in the same main program, and that require for time check to coordinate this I/O. You have to read the input, and also you have to check your backup times, and you have to schedule your I/O, which will complicate your programming. If you use multi-threading, you can decouple, and one can do a backup, one can do a typing. Okay, and backup can do automatically by themselves. Okay, and in a way, this is also synchronous. One is doing in the background, the other is doing. Batch processing, reading the next batch and processing the first batch can be assigned to two different threads, so they can be, even though reading can be blocked for an I/O, previous batch can process, can run it. So you can do also asynchronously. One can still run, the other can do reading, and they can be blocked. And that blocking does not block the first one. Okay, but they can process. They can process. They don't have to wait for I/O. So here there are three threads, two different processes. Okay, they are scheduled interleaved on a single processor. Okay, so you have an example of three threads, and two threads are from process 1. One thread is from process 2. Okay, and there are thread switching. Let's look at how CPU is scheduled in this example. Okay, so first thread A of process 1 is scheduled to processor CPU, but it's requesting I/O. It's blocked. Okay, you have context switching. Since it's blocking, at this time, same process but different thread is scheduled. Okay, there is no I/O, so it runs to completion until its time slice expires. Okay, so here the thread 2 has expired, so another ready thread, so request is complete and thread A becomes ready, and you switch back to thread A of the same process. So thread A is running. In the meantime, a new process is created. Okay, and it's waiting until this previous thread complete. So its time slice expires. At this time, in this process, thread C, another thread, because it supports multi-threading, thread C is scheduled. So thread C is scheduled. So thread A, B, and C, three threads are scheduled onto a single processor. But two threads come from process 1, another thread comes from process 2. Okay, so process is not directly scheduled, thread is scheduled. Multi-thread is done. Okay? Okay, let's look at the thread stage. Like process, it has ready to run or running. So currently scheduled to the processor, or blocked means it's waiting for I/O. Okay. Suspension does not make sense. Suspension here means thread. This means from the textbook. That makes sense. Since suspension involves moving the image to the disk drive, so all the threads should be also stepped out. So it's process level stage, not thread level stage. Okay. These actions, thread operations, affect thread stage. So when a new process is spawned, a new thread, a thread for that process is created if you use multi-threading. So if you create a process, a thread is created. And this thread can spawn or fork another thread, like process before, okay, within the same other space. So threads now can be a parent thread or a child thread. They can create or spawn a new thread. And when a thread needs to wait for an event, it will block. Block means it has to stop. Okay, it is blocked. So it has to save its program counter as registers in a thread control block or thread state. So it has to save its program counter is or general purpose register. It has to save into your thread context. After the blocking, as you have seen in the example, processor may switch to another ready thread in the same process or in a different process. Okay? And unblock means if the waiting event actually occurred, then thread moved to the ready queue. It can ready to be assigned a processor. Finish is like terminate, exit the thread. It has executed all the instructions. When thread complete, you can deallocate all these register contexts and stacks because you no longer execute the thread. Okay, you terminate. Let's look at the remote procedure call using a single thread. Single thread means no thread concept, process. Okay? So you generate two remote procedure calls to two different hosts to obtain a combined result. Without multi-threading. So with a single process, you generate remote procedure call request. And this goes to the server, and you have to wait, okay, until the reply comes back because there is only one thread of execution, one process execution. Wait. When the reply comes back, you process this result and you generate second remote procedure call. You send it to second server. Okay, you have to wait and then get the result and combine. Okay, and then continue. Okay, one by one sequentially. So you have to wait this much, you have to wait this much. This will delay your processing time. Okay, this is single-threaded program model with one process, one thread. That means there is no thread, multi-threading. Okay, single thread means no multi-threading. One process. Okay. So each RPC, remote procedure call, has to wait for a response from each server sequentially, one by one. But if you use multi-threading, you can overlap. Okay? This is remote procedure call using one thread for each server. So each remote procedure call request must be generated sequentially because this assumes a uniprocessor, single processor, but with multi-threading model. So with multi-threading, you generate remote procedure call. You send this request to server 1. You block, but you don't have to wait for response. You can switch to another thread, ready thread, thread B, which generate another remote procedure call request. Send it to server 2. Okay, and you can block. Okay, even if two threads are blocking, their blocking time can be overlapped. You can wait concurrently for two different servers, and as soon as the first reply comes back, the thread can be scheduled to thread A. You can receive this result. Okay, and then the second reply comes back. You can do a context switch to a thread B. Okay, you can receive the second result, and the first thread will be blocked because it's processing the second thread. Okay, and then you can combine. Okay, and continue. Okay, so by doing this, you can overlap this block time, and you can wait concurrently with two different servers, and you can improve the speed. You are on the step top. Okay. Since people are becoming sleepy, I think one student prepared for slides for this Windows priority setup. Who was the student who sent me? Can you do a presentation, 5 minutes?
Okay, I will start my presentation. My presentation for processes priority modification in Windows Task Manager. You can see the task manager when you press the Ctrl-Alt-Delete key in your Windows PC. Generally, process created by system or user has normal priority. Such few system processes have a high priority, like winlogon.exe. That process control the Windows login and logout. That is very important process, so that process has a high priority. But you can change the priority of a process in task manager. As a result of modification, each process has different time slice and dispatching sequence. You can see the example in this picture. Example 1 has all three process has normal priority. So A and B and C dispatched in sequentially, but example 2, you can see that A has a high priority and B and C has normal. There is difference, so A is first dispatching and B is dispatched secondly. But there is a difference in example 1 and 2. So A has dispatched again and there C is dispatching. So that difference make A process execute faster than B and C. We studied that OS kernel mode can modify process priority in last lecture. Explain about that. If you log in with guest account, you can see the you cannot modify priority in task manager if you log in guest account, but it means that administrator account can operate like kernel mode. Just only administrator account can modify the priority of a process. There is an advantage of modification of priority, but there is also problem. There is hazard in priority modification. That is, example is process A occupies all resource of processor. In that case, your processor, if you modify the priority in real time, in that case, your processor can execute only your process A. So any other process cannot handle, and that means system process also cannot be handled. In that case, your PC will be out of control. So you be careful of process modification. My slide's over. Thank you.
Let's move to more deeper level of multi-threading. So let's try to differentiate user level and kernel level multi-threading. First, let's look at user level thread. So this is called ULT, or user level thread. So this multi-threading can be done at the user level without kernel or without modifying the kernel, or it can be done also at the kernel level. There are some advantages of using multi-threading at user level and also disadvantages. And there are also advantages and disadvantages at kernel level. And some approach actually combine both user level thread and kernel level thread. Okay, let's look at one by one. So there are some open source thread library. Using this application library, you can create user level thread. These library contain codes, all the codes for creation, destroying thread, and scheduling thread, or saving and restoring thread context, or passing messages between threads. So using this thread library, you can do all sorts of thread creation, termination, thread switching, and thread communication. But these all thread management is done by the application. The kernel has no idea. It's only at the user level. So using the thread library, you can create a spawner thread. You can create multiple threads. You can schedule, and you can context switch, and you can do a communication. But kernel, there is no mention of thread, no notion of thread. And kernel does not support thread. So it's only done at the user level. And this figure is explained in the textbook. You should read this textbook, but a little bit complicated. But let me try to explain briefly what it means, and you can go back and read the textbook and understand by yourself. So, in this process B, there are two threads. Thread has its own state, and process has its own state. Each thread is a user level thread. Okay? So thread 1, thread 2. Thread 1 is in a ready state. Thread 2 is in a running state. And process is in a running state. Process is controlled by the kernel, but there is no notion of thread. It is a user thread. Okay? So from this state can, from state A, it can go to state B. So here, thread are in the same state, ready. Thread 1 is same ready state. This is running state. The process, it can be blocked. Process can be blocked by the kernel because process from the running state is doing an I/O, and the kernel will block the process, waiting for that I/O to complete, and the process go to the block state. But thread at the user level is nothing to do with the operating system or kernel. We still think that if thread 1 is ready and thread 2 is running, but since it's blocked, actually it cannot be assigned the processor. It's blocked. But at the user level, the thread 2, they think it's running. Because thread state means it's running, but it's not scheduled any processor. It's blocked. Okay? The point is, thread state and process state are independent at the user level, with user level thread, because user level thread are only at the application level. At the application level, thread has its own state. Think it's ready. But when you go back from the ready block state to ready, and it can be assigned and ready, then when its time is on, then thread 2, when this process schedules, this running state can be actually scheduled to the processor. It can be in an actual state running. But before it's becoming ready, it thinks it's running, but it's not running actually. It's running only in the user level thread state. Actual process is blocked. Okay? So the point is, thread stage at the user level is independent, nothing to do with operating system or process state. Also, from state A to, it cannot go to state A to state B, C. So first situation is from running to blocked. Here, running to ready. Okay. So running to ready can happen in process B because if you stop its time slice, it has to be stopped and go back to the ready queue. This is the ready queue. But thread 2 is still in a running state because these are user level states, thread states. It's nothing to do with process state. Thread 2 thinks it's running, but it's actually running. It's in a ready state. When you go back to running, it can actually run and assign a processor. Okay? The point is, process state and thread state are independent. User level state, thread state are just application level state. They think they are running, or they think they are ready. Okay? But the actual process might be in a block state or ready state. Okay? Another situation is from here to here, A to D, from running to running. So maybe it's ready and it's actually running. So actually process is scheduled a processor because process is a unit of scheduling without multi-threading in a kernel. Right? This is operating system. They do not support multi-threading. This is only user level multi-threading. Okay? But thread 2, this user level thread 2 require some actions from thread 1. So ED block is set. So thread 2 go to block stage, waiting for thread 2 complete some action. And thread 2 is in a running stage actually, assigned doing some job. After doing some job, it will complete, and then the event happens, and the block thread can become ready back. Okay, to come back to ready state. But actual process is in a running state. So again, thread states have nothing to do with process state. They are independent. Okay, these are only application level states. They think they are running or blocked or ready, but actual process states are different. Okay, because it's controlled by operating system kernel. And these are controlled by thread library at the user level, and they assign their thread state independently without operating system. OS has no idea of what application level is doing. Okay, these are just user level thread. Okay, it's make it easier to program, but actual performance. So there are advantage and disadvantage using this user level thread. There are some advantages. Thread switching does not require kernel mode privileges. Because those are done only at the user level. You can switch thread, and there are only user level thread, and there are only user mode thread switching. So you don't have to go to kernel and back. Okay? So it can allow faster switching than kernel level thread or other user level, kernel level combined. And because scheduling is done at the user level or application level, you can use any kind of scheduling algorithm for your thread library. So you can tailor your scheduling for your application, your thread library. And operating system schedulers can have their own scheduling for process scheduling. So you don't have to disturb operating system scheduler, and scheduling algorithm can be tailored for the application. Okay? So user level has its own scheduling, and kernel has its own scheduling. And since you don't have to change your underlying kernel, you can run this user level thread library on any operating system. Okay? These are only at the application level library, so you can use user level thread without operating system that supports multi-threading. Okay? So these are advantages. You can do some sort of user level multi-threading at the application levels, and some of them are advantages, but there are some disadvantages of using only user level multi-threading. Typical operating system calls, as he mentioned, many system calls are blocked. If you use system call, you have to go to the kernel, and you have to wait. You have to go to the kernel mode. Okay? So as a result, when the user level thread executes a system call, not only that thread is blocked, but also all the other threads within that process should be blocked as well. Because you have to go to the kernel, and kernel has to process that system call or IO. Okay? And all the threads should be blocked, actually, effectively. And the other disadvantage is if you use only user level multi-threading, you cannot take advantage of multi-processing or multi-core processors. So a kernel assigns only one process to only one processor or one core. Okay? Therefore, only a single thread can be run for each process core. But with the user level thread, even if you had multi-processor or multi-core, okay, the kernel assigns only one process to one core or one processor. So only one thread can run at a time. So you cannot schedule multiple threads to multi-cores or multiple threads, multi-processors. So you cannot take advantage of multiprocessor or multi-core with user level multi-thread. If you use, if you try to use multi-core or multi-processing, then you have to use kernel level multi-threading, which means thread should be a scheduling unit of the kernel. Then you can use multi-core or multi-thread. If you are using user level thread, you cannot take advantage of multi-core or multi-processing. Okay? So, to take advantage of multi-core or multi-processor, you have to use multi-threading. And at the kernel level, this is called kernel level thread. Kernel level thread. And thread management is done by the kernel. And if you use kernel level multi-threading, there is no thread management at the application level. If you try to create a new thread, you simply call API to the kernel thread facility, and this is done at the window, Microsoft Windows. So to create a kernel, you call the system call, and then kernel will generate a kernel thread for each thread. So this kernel thread becomes the scheduling unit of this operating system kernel. There is no user level thread, there is only kernel thread. Okay, that's the kernel thread. Okay. So at the user space, if you want to create a new thread, you simply call API to the kernel, and kernel creates a kernel thread. And kernel threads are the scheduling unit at the kernel. The kernel can simultaneously schedule multiple threads from the same process onto multiple processors or multi-cores. Okay? Because kernel thread is the unit of scheduling at the kernel. You create a kernel, you create a kernel thread, and kernel thread can be assigned a processor or core. Okay? If one thread is blocked, kernel can schedule another thread within the same process. So from the same process, you create 3 threads, and you create 3 kernel threads, and these are all independent kernel threads scheduled by the processors. Okay? So if one thread is blocked, the kernel can switch to another thread. Okay? Either within the same process or 2 different processes. Okay? And if you support kernel thread, the kernels themselves can be multi-threaded. So you can, at the user level, you can call this API, system API, to create a kernel thread, or the kernels themselves can be multi-threaded. Kernel operating system code can be multi-threaded code. There are some system kernel threads and also user-created kernel threads. Okay, with kernel thread. And these all kernel threads are scheduling unit, and the CPU can be scheduled to all different kernel threads. Okay, so you can do multi-threading at the kernel level. Okay? These are the kernel threads. But kernel thread has some advantage because you can use multi-core technology or multi-processing. And if one thread is blocked, the other thread may not be blocked because you can be scheduled by the kernel, because kernel thread is the unit of scheduling. Okay? So there are certainly advantage. User level thread, one thread blocked, the other threads are blocked as well. Here, they don't have to block. The kernel can immediately switch to another kernel thread, because kernel thread is unit of scheduling. But there are some disadvantages of using kernel thread. Okay? Disadvantage: thread switching within the same process requires the mode switch to the kernel. That means you want to create a thread, at user level you cannot create a thread. You have to use system API to ask the kernel to create a kernel thread. So even though same process you create 2 kernel, you want to 2 thread, you want to switch to thread A, thread B, you call system API, create a kernel thread, go to kernel mode, right? And then you create a new thread, call another system API, create a new thread, And then you have to do a kernel mode thread switching, right? So there are these two mode switch to the kernel and then context switching at the kernel level thread. Okay, that's actually slower than just doing at the application level. Okay, even though they can utilize multi-core or multi-thread. So these are two different operations. Null fork means create a new process thread and invoke a null procedure. So forking is, we have discussed that the procedure. By using a fork, you can spawn a new process, like a fork, like a process fork. You can create or spawn a new thread. But to spawn a new thread, within each process, you have to use a kernel API to create a kernel thread. And then invoking a null procedure means at the child thread, right? You can create a child thread. Fork means creating a new child thread. Child inherits parents' all the code automatically, the process image and all the I/O resource. But if you want to execute different code of the child process, you actually load different process image. You can do maybe you can create a new process, but you can do maybe Internet Explorer or you can do PowerPoint or any other process image by loading another process image. We have not studied that, right? That's another subject. I'm not sure we have time, but if we have time, we can discuss. Like process thread can process different process. Here they just simplify null. Null means nothing to nothing. Okay? Instead of parent thread, it's doing nothing. So if it's done at the user level thread, it takes about 34 microseconds. Right? If you use kernel level thread, you have to create kernel thread and then load the image. And it requires a mode switch. So it takes 948 microseconds. So about 30 times slower than just doing it at the user level thread. But scheduling is more flexible because kernel supports multi-threading. But it takes some overhead of calling these kernels and kernel level switch. Okay? So more than an order of magnitude difference between user level thread and kernel level thread in thread creation and this null function execution in our child thread. Signal wait is you send the signal to a waiting process or waiting thread, and the thread wait for that condition. If you're doing it at the thread level, at the user level, it takes 37 microseconds, but at the kernel level, signal and wait, it takes 441 microseconds. So about a little over more than a magnitude slower than user level thread. But if you do it at the process level, another order of more than an order of magnitude slower at the process level. So kernel level multi-threading is faster than process, but slower than user level thread. But there are some advantages. Okay? So you can combine. So you can create threads at the user level using application thread library. And there are kernel space, there are also kernel level threads. You can map these user level threads one-to-one, or many-to-one, or many-to-many by mapping. Multiple user level threads from a single application or single process are mapped onto same number of kernel level threads or a smaller number of kernel threads. And this mapping is controlled by the programmer. Why? To achieve best overall result. If you create too many kernel threads, it will slow down. But there are some optimal numbers that balance this performance. Okay? And you can also take advantage of multi-process technology. The programmer can adjust the number of kernel level threads for particular applications. So multiple threads within the same process can run in parallel on multi-processors and also multi-cores because they support kernel level threads. And a blocking system call did not block the entire process. Okay, so the kernel supports multi-threading. And if properly designed, can combine the advantage of both user level thread and kernel level thread approach while minimizing the disadvantage. If you do user level multi-threading combined with kernel level multi-threading, and because they support kernel level multi-threading, as we have discussed, kernel themselves can be multi-threaded. Kernel routines can be multi-threaded. So this example is known as the Solaris. And we look at Solaris example, how they support combined approach. Okay. And next week, this is Thursday, we will discuss some impact on multi-core and how we can achieve the actual speed up. This is ideal speed up. But if you have serial portion, speed up will slow down at 4.7 on 8 processors. But there are actual overhead in real machines. The actual speed up is only 2.3 or something like that, saturated at around 4 or 5 processor cores. But for database application, they have great attention to reduce this overhead and serial fraction from hardware operating system and middleware and DB application. They can achieve almost ideal speed up for DB application. There are some other applications you can also have good speed up on multi-core technology. And then we look at Solaris. Okay?